So in our previous lesson, we got a general idea of how these related rates problems work and sort of what they mean, but often students struggle with how to actually solve these problems, like what steps to take, particularly when there aren't diagrams that are provided. So in this lesson, I'm going to kind of give you like a framework or some guidelines for how to approach these problems and then how to solve them. But before we get started, let's go ahead and take a deep breath and let's begin. So if I'm being perfectly honest, I don't know that there's anything magical about these guidelines specifically for related rates problems. A lot of the things I'm about to say are really great guidelines for any kind of problem that you're trying to solve, but they are particularly valuable here with related rates. So first step in these problems is to really make a list of the information that's given in the problem. And it's very important that you actually label your variables and your quantities properly. We're really going to want to make sure that we're connecting, like for instance, the radius to the rate of change of the radius. And so you just want to make sure that you're using the same variable when you're talking about the same quantity. It's also valuable that you indicate what the problem is asking you to find, again, using proper notation. Now, a couple of things for you to remember is that when we're doing these related rates problems, you are going to have some quantities and then some rates. And so it's important to remember that when a problem mentions something like a rate or something growing or shrinking or speed or words that are like those, you're almost certainly referring to a rate, which means that it's going to be a derivative with respect to time. Okay. The second thing to pay attention to is you do want to pay attention to whether your rates, and even your values for that matter, are positive or negative. So if something is talking about shrinking, it's probably going to be that rate is negative. If something is growing, more than likely that rate is going to be positive. So make sure that you're sort of thinking about the context of the problem and paying attention to whether something should be positive or negative. So after you finish this first step of making a list of all of the information that's given in the problem and what you need to find, your next question, the next thing you have to do, is to see if you have an equation that links the rates that you're given to the rate that you need to find. And if so, take that equation and then take the derivative of that with respect to t. So if you have a problem that's about the volume of a cube and it's asking about how fast the edge length is changing, well, we have a formula that relates those things. It's v equals the edge length cubed. Or sometimes we write v equals s cubed for side length so that there's no confusion over Euler's number and edge length. So if you have an equation that already links the two quantities that you have, great. You just take that equation and then take the derivative, dv dt equals 3s squared ds dt. And at that point, you have an equation that relates the rates that you're working with. Now, sometimes it happens that you don't have just one equation that links the two of them, and you may need to use two separate equations. Right? So if you have a problem that tells you about how fast the volume of a cube is changing, and it asks you about how fast the surface area of the cube is changing, we don't really have an equation that gives us v as some function of the surface area. Instead, what we're going to need to do is take the formula for the volume of a cube and take the volume for the surface area of a cube and take the derivative of both of them, and then use information from one of them in the other one. I'm going to be going through an example of this in just a moment, but I kind of wanted to point out to you, sometimes you don't have one equation that directly links the two things that you want to talk about, and so that's fine. After you make your list of quantities that you have and what you need to find, write down any equations that are related to it, and then sort of come up with a strategy for how you're going to use those to move from one rate to the other rate. So the rest of this video, the rest of this lesson is just going to be us going through examples, and I'm going to try and sort of follow these guidelines, and I'm really hoping that they're going to help you to make better sense of these problems and give you an idea of how to get through them. So let's go ahead and try those out. So in this first example, it says a cube is shrinking in such a way that the surface area is decreasing at a rate of 6 square meters per second. Find out how fast the volume of the cube is shrinking when the side of the cube is 4 meters. So sort of the first step here is for us to write what we know using proper notation. So as we go through this thing and sort of identify these numbers, right, it says that the surface area is decreasing at this rate, okay? So we might write something like dA dt, A for surface area. So dA dt, the rate of change of the surface area, is negative 6. And then I've got another number over here, right? It says 4 meters, right? So 4 meters is the side length of the cube, okay? So I can write that S is 4. And so to step 1b is for me to list what I need to find, right? The problem is asking me to find how fast, that's a rate, so how fast the volume is shrinking. So this is sort of dv dt is the thing that I want to find out, okay? So I've listed what I know, I've listed what I want to find. Now in sort of like step 2/3, the rest of the problem is, okay, is there an equation that links the rates that I have above? Do I have an equation that links the rate of change of the area to the rate of, do I have an equation that links the area, which is one rate that I have, to the volume, which is the other rate that I have? And the answer is no. And we could actually make one, but I find that the computation on this is actually simpler if we sort of like don't try and make a direct thing. So instead we start thinking, well, I do have a formula for the surface area of a cube. The surface area of a cube should be 6 times the side length squared. And then I have another thing that tells me that the volume of a cube is the side length cubed. And so my thinking here is, I have the rate for the area. I could use this to find the rate for the side. And then if I use that rate for the side, I could use that rate over here to relate it back to the volume. So I'm sort of going to do this in 2 steps, right? And both of these things are going to sort of require that I take the derivative with respect to t and then work through them. So now that I've kind of got a little bit of a strategy for how I want to put these things together, I'll take the derivative with respect to t, right? So this is going to give me dA dt equals 12s ds dt. It's supposed to be an s, there we go. And I know that this one over here, I might as well take the derivative at the same time. This is going to be dv dt equals 3s squared ds dt. And so again, I just want to make sure that you sort of like see the strategy here. We want to find dv dt. I know what s is, but I don't know what ds dt is. So I'm going to find ds dt. I'm going to find this rate by looking at and thinking about this rate equation over here. Okay, so I'm going to plug these values that I have in over here. We knew that dA dt was -6. So 12 times 4 times ds dt. So if I divide this 48 over, I'm going to get -6 over 48. That's -1/8. That's what ds dt is. So now that I have this sort of like intermediate step, now that I know that the side length is shrinking at a rate of, 1/8 meters per second, I can take that and put it in over here. I can find that dv dt, the rate of change of the volume, how fast the volume is changing, would be 3 times 4, 4 was the side length, 4 squared, times that -1/8 that I had just found. Okay, so, working this out, I'm going to have 3 times 16 over -8. The 8 and the 16 will drop down to 2, so this is -6. And if we really wanted units here, we could say that this is cubic meters per second. Okay, so this is sort of what it looks like to use this method. So again, just as a quick recap before we go on to the next one, you start by writing out the quantities that you know using proper notation, write out using proper notation what you want to find, then look at the rates that you have and think about whether you have an equation that relates those two things. If you don't have something that can go directly from one to the other, you can find sort of an intermediate variable to use between them. So in our case, we changed the rate of the area into a rate for the side, and then we use that rate for the side to get at the rate for the volume. So that's kind of our method for how we're going to be working through these problems. So hopefully that made sense. As always, if you have questions, let me know about it, but let's move on to the next few examples that we have so we can practice this some more. So it's worth noting that sometimes problems are going to have multiple variables, like a radius and a height. And I want to point out to you that the existence of multiple variables really doesn't change the guideline from before. So I want to show you through this example that we're going to do the same thing. We're going to start with a list of the variables that we know, and a list, a statement of the variables that I want to find out, or the quantity that I want to find. And then down here, we're going to write down the equations that link the rates, and then we'll solve that. Okay? So this example says the surface area of a closed cylinder is given by that formula. This formula, by the way, totally makes sense. This 2 pi r squared, this is the area of the circle on the top of the cylinder and the area of the circle on the bottom of the cylinder. And then this 2 pi rh is just the circumference of the base times the height of the thing. So if you sort of imagine taking a can and cutting it and like opening it up, this thing turns into a rectangle where the base of the rectangle is 2 pi r and the height is h. Sorry, I got a little bit distracted there, but just kind of wanted to point out to you, like, the formula makes sense. That's where it comes from. So surface area of a closed cylinder given by that. H is the height, r is the radius of the base. At the time when the surface area is decreasing at a rate of this, okay, so right there, we have that dA dt, the rate of change of the surface area, is decreasing. So it's decreasing at a rate of negative 30 pi, okay? So at the time when the surface area is decreasing at this rate, okay, it says that the radius is 2, so r is 2, and the height is 4, and it says, and the height is increasing at a rate of that. Okay, so the height is increasing at a, okay, so we have even more stuff over here. dH dt is, and it says the height is increasing, so dH dt is positive 1/2. So this is all information that we know. And then it says find the rate of change of the radius at this time. Okay, so they want me to find dr dt. Okay, so now our question becomes, all right, do I have any formulas that relate the rates that I was given? So do I have any formulas that have A and H and also the rate that I want to find, R? And sure enough, yeah, it was given to us right here. I have one equation, one formula, that relates the area, the height, and the radius. And so if I just take this formula, this 2 pi r squared plus 2 pi rh, and take the derivative with respect to t, I will more than likely just be able to plug in all of these things and find out what this is. So let's give that a shot. I'd actually really recommend that you sort of pause the video here and take the derivative of this, see if you can plug all these numbers in, make sure that mechanically you're comfortable with what's happening here, so that all we really need to focus on is sort of the setup and pulling all of this information together. So hopefully you've taken this derivative on your own. You've got the dA dt. Remember, anytime I take a derivative of something that isn't t, I've got to have this like dA dt thing, dr dt, dH dt. The derivative of 2 pi r squared will be 4 pi r dr dt. And then over here, I'm going to have this is going to have to be a product rule. I have 2 pi r and I have h. So first, I'll do the derivative of 2 pi r. So that'll be 2 pi dr dt, leaving the h alone, plus, now I'll leave the 2 pi r alone and do the derivative of the h, which is going to be dH dt. Okay? So now that I've got this whole long formula thing here, I'm going to go through and I'm going to plug in all the values that I have. Okay? So dA dt is negative 30 pi. 4 pi, my radius was 2. My dr dt is the thing that I want to find, so I'm just going to leave dr dt. This is just going to be a variable I'm going to have to find. Plus 2 pi. Now dr dt, again, is the thing that I want to solve for. And h was given to us. That was one of our pieces of information, so I've got 4 there. Plus 2 pi, r is 2, and dH dt is 1/2. So notice what I did here is I took the formula that I had that it was relating the variables I had. I took the derivative so that I could look at the relationship between these rates. And now I just plugged in everything I had. Right? dr dt is the thing I want to solve for. So now it's just a matter of sort of simplifying all this stuff and sort of moving it to the same side, or solving for the dr dt. So this is negative 30 pi equals 8 pi dr dt plus, and maybe coincidentally, another 8 pi dr dt plus Now let's see here. Over here, these 2's are going to cancel. Looks like this is just going to be 2 pi. So when I subtract this 2 pi over, I'll have negative 32 pi equals 8 pi dr dt. And when I divide that 8 pi over, I'm going to get that dr dt is negative 4. Okay, and this was all about meters and such, so I could write this as ms negative 1. By the way, I didn't mention this earlier, but this negative 1, this is just sort of like another way of writing negative 4 meters per second. Remember that when you raise something to a negative power, it's sort of the same as dividing by that thing. And so ms to the negative 1 really just means meters per second. That's all that means. So hopefully this has made it clear that even when you have a problem that has multiple variables, we can really use these same guidelines to make a list of the information that we know, write down what we want to find, see if we have a relationship between the quantities that we have rates for, and if so, take the derivative of that with respect to t and plug in the values that you have to work with. Okay. The next two examples are going to be more about sort of the use of diagrams, and so that's kind of where we're going to go and what we're going to look at next. All right, now, an important thing for us to note, for problems that are really clearly about simple geometric figures like squares, circles, cubes, spheres, to a lesser extent, cylinders, a diagram is really not going to be necessary. But for problems that involve motion or where motion where a shape or a figure isn't clear, like a diagram can really be helpful. So in these cases, you start with the diagram, and then after that, that sort of helps you to figure out what the relationship is between your variables, and then you follow the steps that we talked about before. You make a list of what you know, of what you need to find, and then look at finding an equation that relates the quantities that you have rates for. Okay, so an example here. An adventurer is 12 meters west and 4 meters north of a hidden treasure. Okay, so if I've got a hidden treasure right here, X marks the spot, and we know that there's an adventurer that's 12 meters west of that. Okay, so 12 meters west and 4 meters north. Okay, so this is kind of our setup here. And automatically, when you're working with cardinal directions, this is probably going to wind up being some kind of a triangle. So we've got to draw our adventurer here. It's like an adventurer hat. I don't even know, adventurers don't adventure in top hats, but that's the kind of hat that they have. So we now know the adventurer is moving east at a rate of 2 meters per second. All right, so if the adventurer is moving east, it means they're moving this way. So now's when we may need to start sort of assigning some variables here, right? Maybe I want to say that this is x. Maybe we say that this x distance is 12. If the adventurer is moving east at a rate of 2 meters per second, then how would I notate that here? What would we say about dx dt? Right? Hopefully you said that this was negative 2. Now, why is it negative 2? Well, it's negative 2 because if the adventurer is moving this way, then this distance is shrinking. And so because of that, this is going to be negative 2. Okay. Now, it also says that the adventurer is moving north. Okay, so they're moving north. So if I'm going to call this y, that y is 4, what would we say that dy dt is? And we would say that dy dt is 1/2. And again, why is it positive 1/2? Not because it's up and up means positive, but because as the adventurer moves north, this quantity is increasing. And so because of that, it's going to be changing positively. Okay. Now the question is asking, at what rate is the distance between the adventurer and the treasure changing? Well, the distance between them is basically this right here. Right? So this is like z, and I don't know what z is off the top of my head, but dz dt is actually the thing that we're looking for. So, and I don't know that we actually need to make our list of things that we know and things that we want to find. I've kind of got it on my diagram here, but if it helps, you could certainly pull all this information together, right? I definitely want to help you to see that what I'm doing here is the exact same process we did on the other one. The difference is I had to draw this thing, right? dz dt is the one thing that I need to find. Z is something that's missing that I should probably find, but maybe I won't find it yet. Maybe I'm going to look at the rates that I'm looking at here. Do I know of an equation that relates those quantities, the x and the y and the z? I sure do. We have the Pythagorean theorem. X squared plus y squared equals z squared. Taking the derivative with respect to t, I'm going to get 2x dx dt plus 2y dy dt equals 2z dz dt. Okay, the 2's are all going to, I can divide those out, and so yay. So now, as I'm going through and sort of thinking about this thing, I've got x, it's 12. I've got dx dt, it's negative 2. I've got y, it's 4. I've got dy dt, it's 1/2. Z I don't have, and dz dt is the thing I want to find, so I'm not expecting to be able to find that before this. So it's clear that I need to know what z is. So if I need to know what z is, I can sort of come back to, well, even before I took the derivative, x squared plus y squared would equal z squared. So if I plugged in 12 squared plus 4 squared is z squared. That's 144 plus 16. That's what, 160 equals z squared. So z is the square root of 160. And at this point, this is just a matter of solving, right? This is negative 24. This is plus 2. dz dt, there we go. And if I divide this thing over, I'm going to find that dz dt is negative 22 over the square root of 160. I could actually technically stop right there if I wanted to, or I could use my calculator. And using the calculator here, negative 22 divided by the square root of 160 gets me negative 1.74. Okay, so based on how the adventure is currently moving, they are technically getting closer to the treasure, but we know that they're not quite on target for figuring out where this thing is. So I hope that this was a sensible example of how a diagram can sort of help us to see what the known information is and what the need to know information is, so that we can pick the right equation, do the derivative with respect to t, plug values in, and solve. All right, so I've got one more example here that's going to be about a triangle, so let's get into the last example. This one may feel a little different, so stay with me. If you need to, stand up, stretch, take a breath. It's not super challenging, but there's a little bit more to this one. So here's our example, right? An airplane flying over flat ground at an altitude of 2 kilometers passes over an observer on the ground. And so we might even want to sort of like start thinking about this, right? So there's an observer on the ground, and there's an airplane that's up in the sky, right? That might look like a headless person, but I promise it's a plane. All right, so there's this airplane, and the height of this plane is 2 kilometers. Okay, and I should have said that this was at a constant altitude. So passes over this. Sometime later, the distance between the airplane and the observer is 3 kilometers. All right, so now the plane is further along. They're over here, or I suppose it's over here, because again, that's not a headless person. So now the plane's over there, and now the distance between these two things is 3 kilometers. Okay. Now it says the angle of elevation of the observer to the plane is the angle that the observer's line of sight to the plane makes with the horizontal ground. Okay, so if like this is the ground, and again, this person isn't like buried in the ground, I promise, they're just like, they're at ground level, right? This is sort of the angle they're talking about. And so that actually makes me think like, if that's the angle, if this is the angle they're talking about, maybe I should have drawn this differently. Maybe I should have said, here's the observer on the ground, the plane is 2 kilometers up, and the distance between the observer and the plane is 3 kilometers, because then this could be theta. Okay. Now, let's see here. The angle of elevation is to the plane. So, okay. Find the rate of change of this angle of elevation in radians per second when the speed of the plane is 300 meters per second. Okay. Where do I want to put the speed of the plane here? Like, based on the plane's speed, if the plane is going this way, where is that, like, where should I notate that? Where is that going to be? Well, if I decide to call this A, and if I decide to call this C, and I decide to call this side B, the speed of the plane is effectively going to be dB dt. And it's really, really important for us to recognize. I actually just made this mistake and had to come back and re-record this. We don't want to say that dB dt is 300 because the units right now are kilometers. So if I write 300 here, it means it's moving 300 kilometers per second, which is turns out pretty fast. So this dB dt should be 300 meters. 300 meters, that means it's 0.3 kilometers per second. So this dB dt is going to be 0.3. Okay. Now, the problem is asking us to find the rate of change of the angle of elevation. So at this point, I think it's valuable for us to sort of take a moment and write down, like, okay, so what do we know? We know that A is 2. Do I know what the rate for A is? Do I know how much A is changing? Well, we said that this thing had a constant altitude, so dA dt is going to be 0. Okay, what about B? I don't know what B is. I might have to find that out later. So I suppose I shouldn't put that over here because I don't know what this thing is. But I do know that dB dt is 0.3. I know that C is 3, but I don't know what dC dt is. And then over on this side is sort of my list of the stuff that I want to find. The thing I'm trying to find here is d theta dt. That's the thing that I need to find out. So now that I sort of have this list of things that I know and things that I want to know, my next step is to pull together the variables that I have rates for. Do I know any equations that will relate A and B and theta? Are there any relationships or equations or anything you guys know that relate theta and A and B? I know we don't know what B is, but we know the rate for that. And so what's really important here is you're relating the rates. Okay? Do we know anything that relates those things? And the answer is we do. If you think about trigonometry, we know that the tangent of theta is supposed to be the opposite over the adjacent. So A over B. Okay? So I now have an equation that relates those things. My next step has generally been that we now take the derivative of this with respect to t. So pause the video, do the derivative of this with respect to t. Remember that the left-hand side is just a memorized derivative. The right-hand side, you have a quotient, so you should use the quotient rule. The derivative of tangent, secant squared theta d theta dt equals low d high minus high d low, square the bottom. Okay, so at this point, I effectively need to plug in values. And so as I look at this, I realize I've got dA dt, that's good. I've got dB dt, that's good. I know what A is. I'm going to need to figure out what B is, and I'm going to need to take a minute to figure out what secant squared theta is, but d theta dt is the thing that I want to find. So I'm in good shape here. And by the way, here's another b that I need to find out. So I now sort of need to step to the side. I need to step out of this equation and figure out, so what is b? So what is secant squared theta? And it turns out you can do both of those things without a calculator. They're actually both fairly straightforward. So again, I'd encourage you to pause the video, make sure that you can see and find out what these things are. To find b, I'm going to use the Pythagorean theorem. We know that a squared plus b squared is supposed to equal c squared. Working through this, I'll get b squared is 5. That means b is the square root of 5. And so now, I could actually take that and write it up here in my known information. b is the square root of 5. Okay? I don't need to know what dC dt is. I'm really glad I didn't spend time figuring that out because it's not going to be necessary. Right? What I do still need to figure out is what secant squared theta is. Okay? So let's think here for a moment. Secant theta is 1 over cosine theta. And cosine is adjacent over hypotenuse, so this would be the hypotenuse over the adjacent side. So from right here, hypotenuse over adjacent side. So that means that secant theta is 3 over root 5, which means that secant squared theta is going to be 9 over 5. So 9/5 times d theta dt is the b value, root 5, times dA dt, that was 0, minus the a value, that was 2, times dB dt, that was 0.3, not 300, because it's kilometers per second, divided by b squared. Well, my b was a root 5, so b squared would be 5, right? I mean, it looks like I can multiply both sides by 5 to remove those things. And now, I mean, this is just going to come together really quickly. D theta dt, this also turns into 0, is negative 0.6 divided by 9. And that's it. I mean, I don't know that we really even need to do anything more than that. If I wanted to, I could do 0.6 divided by 9 and find out that this is negative 0.06 repeating. Either one of these things is an acceptable sort of expression of the number of radians per second, of the decrease in that angle of elevation as the person sort of watches this plane fly off into the distance. So I know that was a long problem. This one was fairly involved, but I was really hoping to show you that by drawing a diagram, then making a list of what we know, what we want to know, writing the equation that relates the thing that we have rates for, taking the derivative with respect to t and plugging things in, we worked our way through this problem. As always, if you guys have questions about these things, please let me know. Like, write them in the side of your notes, and I'll do my best to make comments on those things, or ask me during class. I wish you the best of luck as you work through and try these problems.